So we will be continuing with our playlist. So before that, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is flatten a linked list. Now you won't be given a generic linked list. The linked list that is given to you will be different in configuration. Let's understand that. When I say that you'll be given a linked list, you will be given the head of the linked list. Generically, the linked list always has a next pointer. So the head will always have an X pointer pointing to a node, an X pointer pointing to another node, an X pointer pointing to another node, an X pointer pointing to another node, and eventually the next pointer will be pointing to null, right? At the same time, apart from the next pointer, this particular configuration will have child pointers, So if you look at every node, it has a pointer pointing down. So the pointer pointing down is the child pointer. Now if you look at the first node, the head, it doesn't have a child node. So the child pointer is pointing to null. If you look at the next node, it does have a child node. So the child node is pointing to, the child pointer is pointing to the child node. And eventually 10 is pointing to null. Now the 10 also has an X pointer pointing to null. Similarly, if you look at 1, the next is pointing to 4, but the child pointer is pointing to 7. 7's child pointer is pointing to 11. 11's child pointer is pointing to 12. 12's child pointer is pointing to null. And all of these nodes have next pointers as well, and they are pointing to null. So understand the configuration. So you'll be given a linked list of this particular configuration. You will be given the head. Each of the linked list node will have an integer in it. And there's one more thing. Every node and its child nodes are sorted. Carefully have an observation. 1, 7, 11, 12 in a sorted order. 4, 9 in a sorted order. 5, 6, 8 in a sorted order. 2, 10 in a sorted order. 3 in a sorted order. Every child linked list is in a sorted order. Now your task is to flatten this into one child linked list. Flatten this into one child pointer linked list. Let's understand this. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So when I'm saying flattening all of these linked lists, because this is one linked list, this is another, this is another, this is another, this is another. So you have to flatten all of them into one. It means you start the head with 1, that points to 2, that points to 3, because you'll have to do it in the sorted order. It points to 4, and so on. It will be pointing to the last one, 12, and eventually to null. And this next pointer will be pointing to null. The next pointer of everyone will be pointing to null. And this will be the head of the flattened linked list. So you'll have to return me a flattened linked list in the vertical order. Got it? So if this problem comes up in an interview, the extreme naive solution that I can think of is take all the integers, put them into an array, and then probably think of a solution. So what I will do is, I will be declaring a list which will be holding all the integers. Then what I will be doing is, I'll be taking a temp and placing it at the head. What is the first value? 3. So I'll be picking up 3, right? Does it have any child nodes? It doesn't have any child nodes. Done and dusted with this one. So what I'll do next is, I'll move temp to the next node. Now what I will do is, I'll be traversing in the bottom direction. And in order to do that, I can take another temp and probably call it as temp2. So temp2 is standing at 2. So I'll be taking 2. Yes, I'll be taking 2. Once I've taken 2, I'll be moving temp2 to the child. And the value is 10. So I'll be taking 10. So once I've taken 10, T2 will be moving to null. Done. Once it is done, I can simply move the temp to the next. So let's move the temp to the next. This time temp has child nodes. It has child nodes. So again you can assign T2. What's the value? 1. So you can take 1 and you can move T2 to the next. So it'll be taking 7 and then T2 can move. It will be taking 11. Then T2 can move. It will be taking 12. So after this, it will be moving to null. So done and dusted. Once it is done and dusted, temporary can move to the next. It is 4. Again, place a T2. T2 is at 4, so you can take the 4. Then T2 will move. It will be taking 9. Then T2 will move. It will again reach null. The moment it reaches null, temp can move to the next. Again T2. T2 can take 5. Then T2 can move. It can take 6. Then T2 can move. It can take 8. Then T2 can again move. It will be at null. So it'll be stopping then and there. And eventually temp will be reaching null. Eventually temp will be reaching null. Once that is done, I have the array, right? What I can do is, I can simply apply any sorting algorithm on them. So I'll be applying any sorting algorithm on them. Once I've sorted them, I'll get a sorted array. So once I have the sorted array, what is the next job? The next job is to convert it into a vertical linked list, not a horizontal one, a vertical linked list. So I'll probably write a convert function that does it. And once I have the head of that updated or the new vertical linked list, I can return that head, correct? So let's start doing it. So what is the first step? The first step is declaring an empty array, right? What is the next step? The next step is declaring a temp which stands at the head of the initial linked list. Let's traverse in the linked list. So I'll be traversing till temporary doesn't reaches null. Quite simple. Initially, we will be having a temporary 2, which will be initially at temp. I'll be going downwards right from that node. So I'll be like, okay, let's go downwards. So I'll be like, while T2 is not equal to null. If that's the case, I'll say, array, can you please add?
I didn't catch that.
Array, can you please add temporary 2 value or data? Once you have done that, T2, can you move to your child? Very important, you'll be moving to the child pointer. You'll be moving child bottom. Once that is done, can I say T2 would have been completed? The traversal of T2 would have been completed. So what I can do is I can say temporary, now can you move to the next because I need the next. So temporary will be moving to the next. Once that is done, I can complete the while loop. So what this will do is, this will make sure that the array has all the elements. Once the array has all the elements, I can simply call the sort function and I can call the array to be sorted. So once the array is sorted, I can probably call the convert function where I pass on this array and it will be converted. It's going to be a super simple convert function. So you need to write the convert function. You already know how to convert an array into a horizontal 1D linked list. You know it. This time you have to convert it into a vertical linked list. This is the change of pointers, right? So what I will do is, I'll write the convert function now for you. So I'll write the convert. I'll take the array. What is the first thing that I'll do? I know that the array has elements. In case the array doesn't have elements, you can straight away return null. In case the array doesn't have elements, which means the size will be 0, you can straight away return null, stating that, okay, you don't have anything, so it will not be storing it. In case it has elements, you'll be declaring a head. You can declare according to your language, and you can call new node array of 0. So this will be your initial head. I need to traverse from I equal to 1 because the 0th index element is done. I'll be going till the last index, which is n minus 1. Again, I'm writing down the pseudocode, not C++, not Java. What is the next job? The next job is to make sure that the linked list is created. So temporary will be assigned to head. And then what I'll do is, I'll create a new node every time new node is created. And that new node will have the value of array of I. Super simple. Very basic things now. Very, very basic things. And once that is done, I'll say temporary, your child, instead of the next. In the horizontal 1D linked list, we were taking next. This time I'll say temporary, your child will be pointing to this new node. Perfect. Once that is done, You can say temporary, you can move to the child instead of next. Super simple. Once the entire traversal is completed, you would have made sure that the vertical linked list is ready. If it is ready, your job is very simple. You straight away return the head. So you have the vertical linked list ready. You can straight away return it. So this will be your brute force. Now, let's analyze the time complexity. What is the time complexity? For ease of explanations, let's assume this particular length is n, okay? And assume each of the linked list is of length m. Each of the linked list, like the vertical linked list that is given to you, is of length m for ease of calculations, okay? So the outer while loop is running for bgo of n times. The inner while loop is running for bgo of m times, vertically once. So the overall complexity in order to traverse and put all the elements will be bgo of n into m, which is technically all the elements, n into m, right? After that, you're sorting down all the elements. So the complexity will be x log x, where x is nothing but n cross m, which is the total number of elements. Perfect. Then you're applying a convert function. Again, the convert is taking all the elements, right? It's taking all the elements. So eventually, all the elements means n cross m. So what is the overall time complexity? Can I say the overall time complexity is n cross m into 2? Why 2? Because you're also using n cross m over here, plus x log x, where x is n cross m. What is the space complexity? Can I say that the space complexity is the array that you're using? And the array is holding n cross m elements, okay? So the overall space complexity is n cross m into 2. Now why into 2? Why into 2? First time, the array that is holding all the elements. The second time, you're creating a new linked list. You're creating a new linked list, new vertical linked list in order to store all the elements, correct? So that will again be taking n cross m. So twice into n cross m. Obviously, the interviewer will not be happy with so much of time and space being taken. So he'll ask you to optimize this. So I need to optimize the previous algorithm. The previous algorithm didn't consider one thing. That is, the vertical linked list are sorted. So maybe I can eliminate sorting from our algorithm if I can use the property of vertical linked list being sorted. The other thing was, we were converting the array into a new linked list. Why do I need a new linked list? It's external space that I'm using. Can I not use the same nodes? Can I just not do it in place? So these two things I'll be keeping in mind. First thing is, use the property that the linked list is vertically sorted. The second, reuse the same nodes instead of creating a new linked list. Okay. First question, what if I just say that you're given this much? Can you solve this problem? Forget about the entire linked list. I'm telling you that you're just given two linked lists, L1 and L2. This is vertically sorted and this is also vertically sorted. Can you actually flatten this? You'll be like, yeah, it's easy. I can do it. What I'll do is, I'll take a T1, I'll take a T2, right? And after that, as usual, we will be taking a dummy node. So let's take a dummy node. And this dummy node will be -1. And the next will be pointing to null. And the child will be pointing to null. Correct? We will start traversing. We'll compare T1 and T2. They are sorted. These two are sorted. 4 or 5, which is small? 4 is small. So I'll take 4. I'll take 4 and I'll place it over here. I'll point the next to null and the child to null as well. And I'll move T1 to the next. Perfect. So what I've done is I've taken 4. And the next job is to compare 9 and 5. I'll take 5. I'll take 5 and I'll place it here. Then again points to null and the child will also point to null. So T2 moves to 6. This time I compare 9 and 6. I'll take 6. Kind of similar to merge to sorted list, but in terms of child. So I'll take 6, point to null, and the child pointing to null. And then T2 will move. This time I'll compare 9 and 8. I'll be taking 8. Yes, I'll be taking 8. Remember, you're using the same nodes. We are using the same nodes. We are not creating any new nodes. We are using the same nodes. So I'll be taking 8, pointing this to null, and the child is pointing to null. And T2 reaches null. The moment T2 reaches null, what I will do is, I'll take this, even if there was 10, I don't care. I'll take the entire thing and make sure 8 is pointing to this. Make sure 8's child is pointing to this. That's what I'll do. I'll make sure that 8's child is pointing to T1, that's 9. And if T1 has anything, it will get linked. Done and dusted. Done and dusted. Can I say this, that L1 and L2 have been flattened into one linked list? I can. And what is that? What is the head of that one linked list? That's dummy node dot child. Dummy node dot child. So I've solved the problem for two lists. Maybe I can write a pseudocode for it, and then we'll try to solve it for multiple lists. So let's quickly write down the pseudocode. Again, it won't be language specific. So we're writing down merge two lists. You're given list 1, you're given list 2. So these are basically head of list 1 and list 2. Again, very similar to merge two list, but those were in horizontal order. Now this is vertical. Got this? What is the first thing? I'll probably assign dummy node. Let's assign dummy node to be -1. So I'm assigning dummy node to be -1. Done. I'll be taking a resultant so that we can traverse through that new vertical list. Taken a resultant. I need to traverse through list 1 and list 2 till both of them or either of them reach null. So I'll be like, list 1, if you're not reaching null, please go ahead. And list 2, if you're also not reaching null, please go ahead. So what is the first thing that you will do? The first thing is, you'll either pick this one or this one. So you need to compare, correct? So the first thing that I'll write is, if list 1 value is less than list 2 value. If that is the case, I'll say that, okay, I'll take list 1. So I'm taking list 1, I'll use the same node again. So I'll say res, can your child, not next, your child point to list 1. Done. At the same time, please make sure that the res is moved to list 1. Done. Once that is done, your list 1 should move to the next. Done. And if that is not the case, we'll do the same with the list 2. Let's do the same with the list 2. So resultant of child will be pointing to list 2. Resultant will move to list 2. And list 2 will move to the next, which is list 2 child. It is exactly the same that we did while merging two lists. It is exactly the same. The only difference is I'm using the child concept over here. So this is done. But there's one thing that you have to keep in mind. Please make sure that res next is null. Because every time you merge, all of these should be null. All of these should be null. Done. Once that is done, you can say that your while loop is completed. At the completion, there's a small check that you have to write. What if there's still a part of list 1 that's left? So you'll ask, hey, res, can your child now go and get connected to list 1? Or else, can your child, if list 1 is not left, list 2 will be left, get connected to list 2. Once that is done, can I straight away return dummy node child, not next, child, because this will be your new head. This will be your entire code. So if I ask you the time complexity, it's going to be BGO of N1 plus N2, where N1 is the size of the first list, where N2 is the size of the second list. Very easy because you're traversing both the list. So we know how to solve it for two lists. But can you do it for multiple lists? Because what you are given is multiple lists. Let's see how we can do that. So we know how to merge two lists. But can we merge multiple lists? I think we can. Let's see how. So you have two lists at the back, right? Can I merge them into one? Probably yes. Just assume that you merged them into one. Just assume. So after this, you can take this one. So this is 1 again. So maybe this one can be considered as L1 and this one can be considered as L2. So these two can be merged as 1. So eventually, you will be able to merge 3 into 1. You'll be eventually able to merge 3 into 1. So now, if I consider this as L1, this one will be L2. Again, can you merge both of them? Probably yes. So 4 of them will get merged into 1, right? After that, you can consider this as L1 and this as L2. Now, can you merge both of them? Yes. So once you merge, the entire thing will get merged into 1, correct? So this is the algorithm that I will try to follow. Let's see how. I'll try to use recursion because I'll try to merge the last 2 at first and make it 1. And after that, once it is 1, once it is a single 1, I'll try to merge with this one and eventually I'll come back. I'll show you how. So what I will do is, I'll start with the head. So the head is 3. So I'll take 3, right? And I'll go deep. So I'll go deep. Okay, fine. So the head goes to 2. I'll again go deep. So the head goes to 1. I'll again go deep. So the head goes to 4. I'll again go deep. So the head goes to 5. Now this is the moment you stop. This is the moment you stop. You see that, okay, 5's next is pointing to null. 5's next is pointing to null. That means it's an individual vertical linked list. It's an individual vertical linked list. So you don't have anything beyond it. So you just return. You return. You return. You backtrack. You return. Now the moment you are returning, what you will do is, you will call a merge. Yes, you will call a merge. I'll write the merge over here. You'll call a merge and you'll pass 4 and 5. 4 and 5. You'll pass it and you'll ask them to merge them into 1. You'll ask them to merge it into 1. So after they are merged, it looks something like this. So when this merge function is called and you're passing the 4 head and the 5 head, they're merging together and this is what is returned to you. It will be returned 4. It will be returned this. So this is where the current head stands. So this is what you return. You'll return the 4. You'll say, okay, take this 4 because this is the merged head. And now again you'll call the merge. But this time you'll call the merge for 1, 4. Why? Because 1 is the head of this function and 4 is what you get back. So you call for this one. Got it? Again, the merge will happen between them. So let's merge it. So once you have called the merge, you'll get the new head. And the new head will be this one. So what you'll do is you'll return that. You'll return that. So once you have returned, your current head is standing at 2. So you'll call the merge for 2 and the new head that you got, that was for 1. So again the merger will happen. And this time it will merge this one and this one. And you'll again get a new linked list. So after the merge is completed, you'll get the new head that is at 1 and you'll try to return it. So once you return it, you get the new updated head. So you'll again call the merge for the new head that's 1 and the current head that's 3. So this 3 and this 1 will go and it'll merge into one new linked list. So once you call this merge function, it will return you the new head as 1. So what it'll return is the new head which is at 1. And this head will be having the entire vertical linked list. And this will be pointing to null, this will be pointing to null. And eventually all the linked list, all the nodes, next pointer will be pointing to null. So make sure you go deep, 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 deep till the last node. And once you return, you merge and return the head. Merge and return the head. Merge and return the head. Quite simple. If I have to write down the function, It's going to be super, super simple. Function takes a head. If it's an empty one, you don't do anything. Or if it is the last one, because that is your base case. That is your base case. If it is the last one, so you can simply check for the last one, stating that heads next. If the next is null, that means you're standing at the last node. If that is the last node, you don't do anything, you return. Because it cannot be merged with anyone, right? So once the base case is completed, what is next? The next thing is, you'll have to go deep. You'll have to go deep just in case the base case is not there. You go deep. And eventually when you backtrack, you call the merge function, right? So you'll have to go deep. Let's go deep now. I'll say function. I'll go to the next. Head of next. Perfect. So when I go, I also come back. So when I'm coming back, what am I getting? I'm actually getting, during the base case, I'm getting the head. After the merge is completed, I'll also get the updated head. After the merge is completed, I'll get the updated head. So can I say I'm getting the merged head in short? Yes, I'm getting that. So when I'm getting the merged head, what is my next job? I'll have to take the current head and the merged head and call the merge. I'll have to do it, right? And once that is done, once I call this will be returning me the merged head, the merged between two lists, and I can straight away return this. Quite simple recursion. Very, very simple recursion. And this one is nothing but this one that we wrote. Got this? So let's do a dry run so that the logic gets straight into your head. What I've done is I've taken a small example. And this one was the code that we did right for flattening a linked list. So initially we are taking the head. And this is the head. So I'll be taking the head. So the head is at 1. The base case is not satisfied because neither head.next is null or neither head is null. So I'll be calling this function. So let's call this function. So I'll be calling this function and I'll be passing head.next. So when I pass head.next, that means I'm passing 4. So basically we are going over here. Got that? This time again, this is not true. This is not true. So the entire base case is not true. So I'll again be calling function of head.next. So I'll again be calling the recursive function. So this time when I call the recursive function, I'll say force next, right? So force next is this one, 3. So I'll be calling it with 3. Head is null? No. Head.next is null? Yes. If you carefully observe, 3.next is null. So the base case is true. So what will happen is, I will return head. So I'll be returning head, which is the head. That's 3. So I'll be returning 3. So what I will do is, I'll go ahead and erase this one. And I'll write 3 because this is what will be returned. Now what is the next step? Merge 2. What is the head? The head is 4 as of now. The merged head is 3. So what I'm asking is, can you go ahead and merge this one and this one? Got it? So it will be merged. So once the merge operation is performed, we'll be getting this one, right? And this 3 will be returned because this is a merge function which will be calling the merge that we have written. We'll be returning 3. So this will be returning 3. So what I can do is I'll go ahead and erase this one and this will be 3. This time, which is the head? The head is 1. The merged head is 3. So what happens is basically you merge this one and this one. So what will happen is this 2 will get merged and you'll get a new head. And that new head will be 1. Once you merge it, you'll get the new head as 1. So this will be returning your new head as 1 and that will be the entire vertical linked list. Got it? How recursion basically goes in and then comes back, backtracking. So anytime if after the recursion call, we're doing something and returning that, We technically call it as backtracking. We're doing something and backtracking it. Got it? So what will be the time complexity? Before analyzing that, let's have some assumptions that the number of horizontal nodes were n, and assume every vertical linked list length to be m. Okay? Now tell me one thing. The small example we took, it had three horizontal nodes, right? Correct? And the recursion depth was 3. It went thrice. And every time I was doing a merge, So every time I was doing a merge. So can I say the overall complexity will be 3? Like in this case, it will be 3 into whatever the merge is taking. Can I say that? I can. This 3 is basically nothing but the horizontal number of nodes, because that is the depth it is going in. So can I say this is n? I can, because this for once, twice, thrice, 3 horizontal depths. Not like for the last time the merge operation doesn't happen, but apart from that, every time it happens. So I can assume it to be 3 into merge. How much is merge taking? If you remember, we did compute it. The merge was taking bgo of n1 plus n2. So since I've assumed the vertical lengths to be m, so can I say it's m plus m, which is bgo of 2m? I can. So n into bgo of 2m is the overall time complexity. Bgo of 2mn, bgo of 2nm, again assuming n and m to be length. What is the overall space complexity? Am I using any external space? I'm not using. Yes, I'm using the recursive stack space. Now this is something which is in memory. This is something which recursion uses. So this is the overall time complexity and space complexity of this particular approach. So going back to the code editor, again you can see that I've written the exact same code over here, and then the merge is over here. And once I've written that, I'll go ahead and click on submit, and it will be submitted. So if you're still watching, I'm very sure that you've understood everything. And if that is the case, please do consider giving us a like. And if you're new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's speed in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken, don't ever forget you're golden.